In the last video, I made the observation that the color shifting ink in certain denominations of US currency relies on the fact that there's a difference of path length taken by light that strikes the upper versus a lower surface. There's a related phenomenon in the world of X-rays. Now here I'm using dimensioning angle differently than you may be used to. There is not a whole lot of consistency in the dimensioning of this angle between textbooks. So here I'm going with the convention that this angle is being measured with respect to the surface as opposed to with respect to the normal. So just be careful about that. Anyway, X-rays are just light. They are very short wavelengths of light, and those wavelengths are short compared to the spacing between atoms in a crystal. So you can use this to figure out the structure of atoms and molecules, for instance. Famously, Franklin and others worked out the structure of DNA this way. Anyway, the idea goes that if I have a plane wave of X-rays coming in on some crystal, we can think of this as a whole collection of parallel rays. So this ray might happen to just scatter off against this particular atom right here. Angle in equals angle out. And so now for some parallel ray, it won't scatter against that atom. In fact, it'll probably miss some atoms, and maybe it'll go down and hit an atom in the second row, or maybe some deeper row. Eventually, each ray somewhere will find something to bounce off of. In any event, this ray here will have traveled a longer distance than this ray here. In fact, this bit right here is the extra distance traveled. So if we want to have constructive interference, we need this extra distance traveled to be equal to some integer number of wavelengths. So what is this extra distance traveled? Well, this line right here, this would be the spacing between the atoms, d, and that's also the hypotenuse of our triangle here. This angle here is also theta, so that means that the extra distance traveled would be equal to d sine theta. But there are two of these segments, so we'll need that 2d sine theta equals m lambda. And by studying the scattering angles of the X-rays, you can work backwards what the structure of the atom or molecule had to be. Actually, before the days of computer software making that particularly straightforward to do, a old school way of doing it was to take a whole bunch of ball bearings and space them using styrofoam, and then scatter microwaves off the ball bearings. It was just basically a giant scale model version of the same thing. Arrange the ball bearings until the microwaves scatter exactly the same way that the X-rays did, and you figured out the structure of the thing you were looking at. Okay. So with that, I want to segue into single-slit diffraction. And to start with, I am going to make an observation that the layout of virtually every small tourist trap coastal town in northern lower Michigan looks pretty much the same, is actually for a physical reason, believe it or not. So when you go and look at a typical tourist trap town near a Great Lake, so let's say there's the beach there, you'll have a highway here, and then coming in along the beach will be a breakwater that was built by the U.S. Army Corps of Engineers to make it safer for boats to enter and exit the harbor over here. So if you go and sit, usually the road is set back a little bit from here. And so in this stretch right about here, and I want you to notice that it's not perfectly lined up with the entry and exit points of the breakwater, will be the village park. And then usually there will be, over here will be some public docks. And over here will be a private marina or something like that. And then usually on the other side of the street from the park, you'll probably have yourself some sort of kitschy strip mall. And then over here, more toward the public dock side, will be a tiny little building left over from the 1950s. That is where the Dairy Twist is located. There's also probably a little playground in the village park somewhere. You get the idea. But this sort of structure here turns out to have a lot of physics dictated behind it. As water waves could come in, it turns out that when you put in the breakwater, it doesn't completely shadow the waves straight behind it, and we'll get into why that is in a second. It turns out, though, it kind of shadows out a region maybe looking like this. And then there will be over here and over here, there will be some waves, but they will be much, much lighter than the waves that are coming in hitting on the village park over here where the beach is. So we can now go ahead and just transition this to light, but the whole point, and take it from there. So let's say I shine a laser beam onto a single slit, so much like the breakwater that we might have on our docks in the water analogy. So a plane wave is coming in on my slit, and I look over here. Oops. And I have a viewing screen over here somewhere. Again, the slit will be very small compared to the separation, but I need to get this all to fit in. What you'll find is that there will be some dark bands. So this would correspond to my first interference minimum. And it turns out, so let's go ahead and say that the separation of our slit, the width of our slit here is A. It turns out what you can do is you can look at pairwise points, like say this point here and this point here, and realize that this extra distance traveled by the lower one has to be an extra half a wavelength. And you can do the same thing with any other pair of points. Sorry, I was trying to write an A there for the slit width. And it turns out you can do the same thing with any other pair of points that you like, as long as that pair of points is also separated by width a over 2. It'll turn out that, say, again, this one will have the extra lambda over 2. Now, most of these points will repeat off pairwise. There'll be the ones I drew with the x's is the only one where you could get fit a third one in. And it doesn't really matter that we can fit that third one in, except it makes it a little easier to think about. So I'll just go and put this one in here. Then we realize if this one was an extra half a wavelength, then this one will have to be an extra entire wavelength compared to the first one up here. We can do our trick that we did before of saying that all these rays are very nearly parallel. I know it doesn't look like it in the illustration, but this is because I'm greatly exaggerating the width of the slit for clarity's sake. Anyway, we can then go ahead and drop a perpendicular and say that this extra distance has to be equal to m times lambda. For the first minimum, lambda would have to be 1, and so forth. Turns out that the condition for minima, so for destructive interference, will again be that a sine theta equals m lambda, and usually theta is small, allows us to rewrite it as theta equals lambda over m, like before. Except before, when we did this, this was for Young's experiment, and that was locating where like the first, second, third, fourth maxima were. Now we're locating where the first, second, third, whatever minima are. So we're, with the exception of the central max, because there is still a central maximum here, with the exception of the central max, wherever Young's experiment has maxima, in single-slit diffraction, we would have minima if we had a slit the same width as the separation of the two slits in Young's experiment. Now, the two effects can combine. Typically here, the single-slit diffraction pattern will be substantially wider than a Young's experiment pattern, because the slits would be narrower than the slit separation. But what winds up happening in a real-world double slit experiment is you get the single slit diffraction pattern superimposed on top of the double slit pattern, and so some of the peaks will be brighter and some will be dimmer. I consider this be beyond the scope of this presentation, but I figured you should be aware that that does happen when you actually do the experiments. So I think it's probably a good idea to do an example of this. Oops, sorry about that. There we go. So the example I have in mind is, let's say that we found that the second minimum was located at 0.70 degrees for a slit that was 0.10 millimeters wide. I'd like to know what the wavelength of the light is. Well, we can go ahead and use the relationship that we just had here. 0.7 degrees is certainly a small angle, so we can use the small angle approximation. So we can start with theta equals lambda over m, rearrange that to get that lambda is or sorry, I dropped an A there, my bad. Theta equals lambda over MA. Wait, worse. Theta equals M lambda over A. Sorry about that. So let me fix that down here too. Theta equals M lambda over A. So theta will be, lambda will be equal to A theta over M. Okay, so let's just go and start putting everything in. I can say lambda here will be equal to, okay, 0.10 millimeters. You'll probably want to convert that over to nanometers. There's a million nanometers in a millimeter. And now here we got to be really careful. 0.70 degrees, but we need to work in radians. So we remember that in 180 degrees, there's pi radians. And then we can divide it by 2. Alrighty, so let's go ahead and crunch that out. So we will have 0.1 times 1 times 10 to the 6 times 0.7 degrees times pi divided by 180, and then we divide by 2, and we get, hey, okay, that's indivisible, sounds good, about 611 nanometers. And so this is a way that we could measure the wavelength of some unknown light. Okay, in the next video, we will extend this idea to what if the aperture has a circular shape, and then we will see what effects that will have on the resolution of optical instruments. So catch you in the next one.